My name is Aleksandra Sretenovic. I'm teaching assistant at the Department of Thermal Science at Faculty of Mechanical Engineering. And the other two co-authors of this paper are Professor Branislav Živković, also from the Department of Thermal Science, and Professor Radiša Jovanović from Automotive Control. I will tell you about regression models, support vector machines, and neural network model for prediction of commercial building energy consumption. So, considering that in Europe, buildings account for 40% of total energy use and 36% of total CO2 emission, the estimation or prediction of building energy use is becoming the topic of greatest interest. In literature, you can find various classification of these methods, but the one that I found most suitable is dividing them into three categories. First one is white box methods, black box, and gray box methods. When we speak about white box methods, they basically come down to using physical techniques to model the building behavior. So they are more or less solving the thermodynamic equations using various softwares that are developed in this purpose. And those softwares are DOE, Energy Plus, Transys, HAP. There are a lot of softwares available on the market. The downside of these models is that you need extensive knowledge about the building characteristics and system parameters. And the problem is that when the model is not calibrated enough, it cannot predict the building energy consumption with great accuracy. And then we have black box methods that are basically statistical techniques that are used to make some connection between the input variables and output variables, which the downside is it is required that both input and output variables are known and measured, which is usually not the case, especially with the old buildings. And also the downside is that all of those models are like black box. You just know the input and output, but it's very hard to physically interpret what is happening inside of the model. But they show much better accuracy in prediction than the other methods. And we have the gray box method, which are the combination of black box and white box methods, which try to overcome all of the shortcomings of each of these methods, but keeping their advantages. So, artificial neural networks are a computational intelligence technique. It is one of the most popular artificial intelligence methods that are used for also in automotive control, usually in pattern recognition, but lately also for the prediction of energy use. They are based on the information processing system of the human brain. They try to mimic the activity of the human brain. So they belong to the black box methods. Their characteristic is that they learn the relationship between input and output variables based on the historical data. So again, it requires a huge amount of real measured data. Usually they consist of input layer, output layer, and one or more hidden layers. And the nonlinear activation function in hidden layer is the one responsible for enabling neural networks to be a universal approximator. The other artificial intelligence technique, which is maybe a little bit less known, is support vector machines. I will not speak into detail about the mathematics behind these models, but I would like just to point out the difference between these two methods that are most commonly used. Support vector machines was developed from theory. The theory was set up by Vapnik and the co-authors during the 60s years, so 50 years ago. But until recently, they didn't find their application so much. But in recent papers, they show that have the same or even better results in accuracy comparing to the neural networks, which followed a different path. So neural networks were first developed for the application, and the theory came after that. The solution of support vector machines is always unique and globally optimal, which is one of the important advantages of the support vector machines. Because neural networks have the problem with stacking into the local minimum, and also the problem which is usually the problem with the statistical methods, the overfitting. Basically, it means that The model works very well with the training data, but works poorly with some new data that you import into the system. So in order to deal with the statistical methods, you need some database. In this case, the database was created using the software. So these are all simulated data. I chose one typical commercial building in Belgrade, which consists of the ground floor and 4 floors. In total, there are 5,000 square meters of area. The chosen system is a 4-pipe fan coil system with central preparation of a fresh air in air handling unit. The source for heat is gas boiler, and source for cold water is air-cooled water chiller. All the simulations are done using our analysis program, HAP, developed by Carrier, based on the Asher Foundation, and it is used for yearly cooling consumption. I chose cooling consumption for the analysis because of the dynamic of the heat transfer and transient heat transfer. It is much more complicated to calculate the cooling load and even more to predict the cooling consumption of one building. So after one parameter analysis, the variables that most strongly influence the cooling consumption are chosen, and they are varied into some range. So I chose windows area, actually percent of windows in outside wall, which was varied from 20 to 60%. Then specific installed lighting power varied from 5 to 35 watts per square meter, and window shade coefficient varied from 0.15 to 0.9. So in total, there are 245 simulations performed, out of which 200 simulations are chosen for training the statistical models and 45 for testing. First model is multiple linear regression model. It is the simplest model. It just correlates the consumption with the input variables. And because of its simplicity and ease of use, sometimes it still can find its application for energy use estimation in early stages of energy planning. So here, and for all the statistical models, the output is yearly cooling consumption, and the input are these 3 parameters, building parameters. So after the statistical analysis, we achieved the equation, which can later be used for the prediction of cooling consumption. On this graph, you can see the comparison between the modeled cooling consumption and the one predicted with the linear model. Next one is neural network model, which was developed using neural network toolbox in MATLAB. Here we have the model consists of one input layer, one output layer, and one hidden layer, while the best results are achieved with 12 neurons in hidden layer. So I need to say just that all data for the statistical models needs to be scaled in range from 0 to 1 or -1 to 1 in order to avoid that the variable with the greater numerical range dominate those with the smaller numerical range, and also to avoid some difficulties that can appear during the calculation with bigger numbers. The other model was support vector machine model, which was developed using a library for support vector machines, which was developed by Chang and Lin. The optimal parameters are obtained by grid search method, which is one of the advantages of support vector machines. So the advantage is that you have only 3 parameters that needs to be predefined. So the grid search means that you define the range into which you will vary every parameter and the step. So basically it creates the combination of all possible combination of the parameters, simulate for each one, and select as optimal parameters the one that have the minimum error. So comparing to neural networks, it is maybe easier to get optimal results, because for neural networks you need more parameters to be known before modeling. Those are like training algorithms, a number of layers, a number of neurons in hidden layers, which cannot be simultaneously chosen. So neural networks are more trial and error method comparing to, for example, support vector machines, when you can find the optimum parameters using grid search method. So before commenting on the results, I want to point out that these results are based on the software modeling. So all of these all of these values are simulated. So it was expected that the artificial intelligence methods will have great accuracy with prediction, because basically every simulation is solving of some sort of, however complicated, but mathematical equations, and the black box method tried to find the mathematical relationship between input and output variables. So here we can see that multiple linear regression model showed the error of 9.15% during the test period, while neural networks show error of 1.23%, and support vector machines, which are introduced into the prediction modeling lately, show even better accuracy. That's why on this graph you can only see the error that is made by the linear model, while the neural networks and support vector machines show almost perfect match. Of course, it is expected that using real measured data, the error should be bigger. The error will be bigger. But the main idea of this paper is just to show, not to compare models between themselves, just to show that artificial intelligence can be very successfully used for this kind of prediction. For example, if you create once when you create this model using the black box method, any engineer or any energy manager can use this to predict cooling consumption without the necessity to know in detail softwares for simulation. Of course, if you expand the here I have only 3 input variables, but if you expand it with more and more input variables, then your model can have a very wider use.